wait for you to. All right, very good. Okay. So if you look around yourself, virtually every piece of material that you see is inhomogeneous, right? I mean, metals are polycrystals, wood has this very complex structure, concrete has this incredible structure, fiber reinforced composites, and you can keep on going on and on, including the kind of architected materials that a lot of people talk about today, right? So but what is really interesting about all of this is that the features that you see are on a scale much smaller than the scale of the application, right? So the question really that we're interested in asking is the following. Can I take this heterogeneous material and replace it with an equivalent material which is homogeneous? The idea is that the scale of application is much larger, so my application doesn't see all the fine details of the microstructure. And so the question that I'm interested in asking is whether I can replace this heterogeneous material with a homogeneous material. So what I'll try to cover is ask if the answer to this question, whether we can replace the material with an equivalent homogeneous material, is yes. We'll ask what is the effective property, and can you try to understand what is the range of behavior that you can get? I'll actually emphasize the first and then not so much in the second. And there'll be examples where you'll see that you can't quite do that, or you'll have to do that with some subtle features. And that's what I will try to talk about mainly today.
Yes.
Given that this is kind of an hour and 15 minutes, I'm not going to try and do any comprehensive theory, but what I'll do is hopefully provoke your thought by giving you very simple examples, which are somehow contradictory when you first see them, and then hopefully that'll inspire you to kind of think harder about these things. And in the end, towards the final examples, I will talk a little bit about contemporary research in this area, again, through these examples. So much of the examples will be examples. Much of the lecture will be examples. And okay, so let me get started. There are a few ideas which I want to kind of introduce up front. And the first is the following, which we all learn, but we never really appreciate. And the statement is the following. Suppose you have a smooth function. It doesn't mean that its derivative is going to be smooth, right? Derivative of an approximation is not an approximation of the derivative. And that's really what makes much of the examples that I'm going to talk about work. So let's think of this very simple function, f of epsilon. So it's some smooth function, f of x plus epsilon sine x over epsilon. And you see that as epsilon becomes very small, you kind of become more or less a smooth function. There's some small wiggles, but it's more or less smooth. So you can approximate it by this smooth function, f of x. But if I differentiate it, you'll see that the fluctuations are order 1. So no matter, even if epsilon goes to 0, in the limit, you get something which is extremely highly oscillatory. So, and you can never really approximate the derivative with the derivative of the smooth function. And that's what we will see happens in much of the heterogeneous materials. They're going to be fluctuate. The displacements might be smooth if I'm doing mechanics, but the fluctuations in the gradient, in the strain, in the velocity gradient will be very, very high. And much of the behavior of this material will be determined by this fluctuation rather than the smooth field. So that's what I have to try and understand is what happens to these fluctuations. Okay. The second idea I'll introduce is something called a representative volume. So if I have a heterogeneous material, and if I'm using an application, there is some length scale on which I don't see the fine details. And that's kind of the smallest volume on which you see that is what is called a represented volume. So if I go smaller volumes than that, I will see the fluctuations in the material. So there's this notion of a representative volume, which is kind of the smallest volume in which you can replace the heterogeneous material with a homogeneous material. So what we do is really try to do this in an asymptotic sense. So we'll see a lot of asymptotics of something going to zero, as I did in the previous slide. But really, in my mind, what I have is when I say epsilon goes to zero or some microstructure length scale goes to zero, what I have in mind is really that I'm going to sample something about this representative volume. And anyway, if you want to do computation, you have to pick a volume, and that's again gives rise to this notion of a representative volume. Now, though most materials tend to be random, it's useful to think about periodic materials where the microstructure is periodic. And I will try to point out throughout the lecture in examples where randomness and periodicity give rise to the same results. The periodicity just makes the calculations easier, and examples where randomness and periodicity look very different. All right? So, okay. So the final thing is I talked about we'll do asymptotics. And this is this notion of a scale separation, right? So one of the things we'll talk about a lot when we do asymptotics, and you already saw this in the lecture that you had from the professor, is that you do asymptotics of the length scale going to zero. What it really means physically is that we are considering large bodies. So it's not that the microstructure scale is fixed, right? I mean, so if I look at a piece of concrete, for example, the length scale of the pebbles and everything is fixed. What we're looking is larger and larger bodies. However, it's harder to do analysis when you're taking this larger and larger bodies. So we rescale everything to a finite domain of length 1. And in that case, the microstructure scale becomes small, right? So when we say epsilon goes to zero, it doesn't mean that the microstructure, the material scale is somehow becoming small. What we mean is that we are considering larger and larger volumes, and that's relative to the macroscopic volume, epsilon is small. Okay. So I'm going to pause here and ask if there are questions or comments.
Yes. If you replace a heterogeneous material with a homogeneous material, how do you account for unique failure points due to the random structure of the material?
So that's exactly what I mean by I'm going to point out examples where periodicity and is not and randomness give rise to the same thing. Periodic homogenization and random homogenization will give rise to the same answer. And I will give you examples where they don't give rise to the same answer, right? There is some deeper mathematical theory we can invoke. Roughly speaking, when the behavior is averaging, like we see in elasticity, it doesn't matter whether you do periodic homogenization or random homogenization. But on the other hand, when you do things like failure and when you do things like waves, periodicity versus randomness gives you very different behavior. And we'll see that in the examples down the road. Okay?
Thank you.
Let me launch in. So I think Karthik already covered this. So I'm going to quickly recap. So suppose I have what is called an almost periodic material. So that's kind of a generalization of periodic. So you can think of some function like this, right? Where if I look very closely on the small scale, it looks periodic. If I look at the small scale, it kind of looks periodic. But over large length scales, you see that the kind of unit cell changes, right? So here's an example of an almost periodic microstructure. And the idea here is that somehow, if you look at materials, the microstructure may change if you look at many different places. And so you want to try and account for that. And that's one way you do this. Okay. So we're going to assume that I have an almost periodic microstructure. And I have an elliptic problem. In this case, I took conductivity. So C is the kind of conductivity. So you can think of this as a matrix, right? If the material is generally anisotropic, your equation is basically this. So this is C times du dx. If you think of U as the current, du dx is the, U as the electrostatic potential, du dx is going to be the electric field. So this is going to be the basically current. The divergence of the current is whatever source you have, right? So that's your equation. So now we're going to assume that epsilon is small. That means that if I fix x, if I look at some point, there's some periodic medium with a period epsilon, and epsilon being small means that this microstructure is small compared to the macroscopic properties. What you can show in general, and you actually don't have to do periodic in this case, you could do much more general classes of microstructure. What you can show is that the solution of this problem converges in some average sense, and I will make this precise in a second here. So when I say converges, I say that the potential converges to U0 point-wise, but the gradients don't necessarily converge point-wise, but they converge in some average. So if I take the gradient of U, epsilon, multiply it with some smooth test function f, integrate it, that is going to converge to gradient of u0 times f. So it's really convergence of an average. So it's not converging point-wise, and it's only converging on an average. So the example that I'd given you before out here, right? The example that I'd given you here is exactly an example of such a convergence. You see f epsilon is converging to f, but the gradients are not converging. But if you actually average the gradient over some volume here, you'll get exactly the gradient here. So that's the notion in which it's converging. It's called convergence in some Sobolev space. So what you can show is that if you can show that the solution to this equation converges to the solution of the following problem. So you basically replace the C epsilon with some C star, and then you solve this problem. And basically, C star is given by some formula here, which depends on solving the unit cell problem, right? So you apply some average field E hat in certain direction, and then you solve this problem, and then you get basically C star, right? So that's and my understanding is that Karthik actually went over this using two-scale expansion. So what it tells you is that I can replace this medium with a homogenized medium which has a conductivity C star. It also says that actually, if you really want to solve a problem in this medium where it is large compared to the kind of epsilon, don't try to, there is no need to kind of figure out the fine details. You just basically solve it with C star, which is the effective property, and then you get a much smoother solution. And the solution of this problem will actually represent the solution of this problem. So in many ways, the behavior of these materials will more or less be equivalent. So the formal two-scale expansion goes back to Sanchez Palencia, and then there's a very nice book by Benson Leonce Papanicolaou. Rigorous proof. There are various versions of the rigorous proof. And as I said, you can actually extend this to random microstructure. I should have mentioned that is Hashim Strickman and Willis. And there's okay, so if you're more interested in the mathematical side, there's a very nice introduction by Ciranasco and Donato, which actually does not only the formal part, but also the rigorous math proofs of this. But this is a very simple example where I can replace this almost periodic medium with a kind of slowly varying homogenized medium and replace this conductivity with an effective conductivity C star. There's another way of trying to characterize this. There's an equivalent way. So I characterize this by solving the differential equation on the unit cell, but you could have also characterized this by a variational principle. Elliptic problems, linear elliptic problems have a variational principle associated with them, and so the effective property also has a variational principle, and that's basically given here. So you can calculate C star by solving, by basically averaging over a unit cell and minimizing over all possible periodic functions. Or you can use the dual variational principle. So if you have, it's kind of the complementary energy principle where you can characterize the inverse of the conductivity matrix by by minimizing it over all kind of equilibrated fields. So these characterizations are very helpful. And one example of this is that you immediately get a bound that C star is going to be less than or equal to the average of C star. So the average, if I just took if I just took an average, that would give me an upper bound to what the actual effective property is. And if I took a harmonic mean, so the average of the reciprocal, that gives me a lower bound on C star. So C star is bounded by the harmonic mean on the lower side and the arithmetic mean on the upper side, right? So that's a good way. So there are many such variational principles, and there are many such bounds that you can derive. And if you're interested, you should look at Graham Milton's book. It's about 500, 600 pages of many different examples of variational principles and bounds. So, okay, so so that's about kind of the linear elliptic problem, and you had already seen this before. So I now want to move on to other examples, but let me again pause here to ask if there are questions.
I had a question. If we're looking at the weighted integral of the gradient, the one which converges, we multiplied the gradient with some function f. Are there any conditions over that f, or would that work for any?
So if I wanted to be technical, I would say that f has to be square. Actually, all that you need is f to be square integrable, right?
Okay.
But here's the technical part. I mean, because smooth functions are dense in square integrable functions, any smooth f will do. So in fact, the statement is that this convergence should hold for all possible smooth f's. Okay?
Understood.
So this is called weak convergence in this case, W12 or H1. So I mean, in kind of PDE theory, weak solutions means you multiply you just hold it in some integral sense. And so weak convergence is that it converges only in some integral sense and not pointwise. Forget. And the two-scale expansion that we use to kind of prove this is an example of weak convergence again. Okay, so this was conductivity, and as I remarked here, it works essentially the same way in linear elasticity. So let's try to ask what happens if I do finite elasticity, right? So nonlinear problems. Now, in finite elasticity, there are two ways you can pose the problem. One is by writing down the equilibrium equation, which is highly nonlinear. And one of the great kind of fun things about finite elasticity is that your equilibrium equation might have multiple solutions, right? And which is why you have buckling, for example, you have bifurcations, buckling. So you can't do the kind of two-scale convergence that I mentioned below. You have to you have to do it in some variational sense. And so what it tells you is the following. So a typical problem that you will solve is if you are given W as a function of F, which is the deformation gradient Y. So that's how we would characterize finite elasticity, or what is called hyperelasticity. Now the material may depend on X, and I'm only going to do periodic materials now. So what you want, so typically you would specify the problem in this way. So you say that so if I want to solve this problem, what I would do is I would take this total energy and I'll like to minimize it subject to some boundary condition, right? So that's how we would typically pose a problem in hyperelasticity. You could write down the equilibrium equation, but that may have multiple solutions and may not have solutions to. So what we do is to characterize the effective property, we characterize it in this way. What I want to do is to replace this W, which is oscillating on a scale epsilon, with some effective W star, which is smooth, which is in fact does not depend on X because I have only a periodic material, right? And so you can show that there is such an epsilon star. Not only that, you want the solution of this problem to converge to the solution of the effective problem. And this is a notion called gamma convergence. So it's a notion of convergence of solutions. I won't spend too much time on this because I want to focus on what the kind of physics of what is happening here. And when you try to prove this, you find that the effective property is given by the following problem. So just like we had this variational principle for a unit cell, it says, okay, the same thing. That you take your average F, you add some periodic function, and you minimize over all possible periodic functions. However, you have not only got to do this over the unit cell, but you have to do this over all possible multiples of the unit cell. So the effective property is not determined by a unit cell, but all possible multiples of the unit cell. So what does that mean? That means if I look at this, if I just take one unit cell, the microstructure is periodic over it. If I take 2 unit cells, the microstructure is also periodic over this. I can redefine my unit cell to be twice the original unit cell, or 4 times the original unit cell, or 10 times the original unit cell. And that's the medium will still remain periodic in that. So what it tells you, this formula is telling you, is that not only do you have to take this over the original unit cell, but all possible unit cells. So you have to define multiple effective properties, and you have to take the kind of the one which is the smallest amongst all of them. So if W is convex, as it was in the linear case, then you can reduce it to a single period unit cell. But in general, if W is not convex, and in finite elasticity, the energy is not convex, it's only quasi-convex, you cannot do this. So let's try to think about the physics of this. So what happens is the following. Suppose I have a unit cell, suppose I have a microstructure which looks something like this. And suppose I try to compress this microstructure. Right? Now, if I take a unit cell, which is just the single one, I will get an effective property. But if I take 4 of these as a unit cell, then what I'll see is that basically, if the blue material is stiffer than the red material, you can have some buckling internal buckling modes, right? So these blue things can, and this will be much softer than each unit cell deforming exactly the same way. So in other words, this is a test for, so by homogenizing over this unit cell, I get a much softer response than by homogenizing over the original unit cell. Same thing happens here, right? I mean, if I take a medium with yellows are the holes and I try to compress it in 2 directions, it turns out that the test function which gives you the lowest energy gives this kind of period doubling. Much of this was the work of Nicholas Triantafylidis. The original work of this goes back to Nicholas Triantafylidis, who used to be a professor at the University of Michigan in the aero department a long time ago. And then here's a very nice experiment by Katia Bertoldi and Mary Boyce when Katia was a grad student. They made this very soft material, and then they started compressing it. And you see that at some point when you compress it, you end up with this kind of period doubling experiment. So this is really a consequence of the fact that the energy is not convex, and therefore taking a larger unit cell may give rise to a very different homogenized behavior than taking an original unit cell. Okay, so now in this, notice that such kind of behavior depends very much on the clear periodic arrangement of the material. And here, a random microstructure would behave very differently compared to a periodic microstructure. Right? So this kind of exploiting supercell instabilities is really one of the ways people are exploiting this. They call this mechanical metamaterials, but this is really an old phenomenon of buckling revisited in a heterogeneous material. Okay, so in this case, when you have these kinds of small scale behavior, when you have this kind of nonlinear behavior, you very often end up with a very different notion of effective property. And it's never quite clear what your unit cell should be because you can have very long range instabilities. So one way of thinking about this is that you really cannot assume that there is an averaging or separation of scales because you can have long-range instabilities. There are many other examples of this kind in finite elasticity. Questions? Okay. So one question I can ask is the following, that I'll ask the following question. So suppose I look at any one of these microstructures, right? If it were linear elastic, I could study homogenization and use this unit cell. If I have large deformation, I might have these kind of period doubling and other instabilities. So how do I deal? So is it true that at small deformation, the behavior is always given by a single unit cell, even in the finite? So in other words, if you look at this experiment, for example, you have to apply a certain load before you had this kind of period doubling instability. So the question is that generally true? And there's a remarkable work by, okay, so here's some examples in real materials being crushed. Sorry, before I go to that statement. So you can see that if I make a lattice-like material and you start applying a compressive load, now the period has doubled and doubled and doubled. So it's actually the entire specimen length, and you form these kinds of shear bands. So this notion of homogenization goes away in non-convex problems. So you might have instabilities which go completely across. So you don't really have a representative volume when you look at materials in finite deformation. Okay? So coming back to the question I was just posed, right? So whether it is this material or this material, if I look at if I were doing small deformation elasticity, I would say, hey, listen, I have a unit cell. But if I do finite elasticity, there's no unit cell. So there's a question as to whether I can use the small deformation elastic modulus if the deformation is small, or does this instability really happens very early? And there's a remarkable work by Nick Triantafylidis along with Gimona and Mueller, and it says that homogenization and linearization commute. What that means is that if you were small enough deformation, you could use a single unit cell, and it's only at large loads that you might have buckling. And therefore, that leads to this notion of a failure surface or a first failure surface in these materials. It says, hey, listen, look at the unit cell, look at its behavior. At some load, you would get these instabilities. So for example, if I were to look at this problem here, and these two stretches, this kind of the ratio of the stretches in the two directions are lambda 1 and lambda 2. So you see at the lambda 1, lambda 2 equals 1 is exactly where there is no deformation. And you can begin to see the various instabilities happen exactly along these lines. So when you compress it in one or more directions, right? So if you're working in this region with this material, you can use this notion of effective property by looking at a unit cell, but you should always be aware that there is some kind of failure surface on which the material will buckle, and you have potentially long range or period doubling instabilities. So when you go away from kind of the linear behavior, even in something like elasticity, you have homogenization for small enough loads, but you do not have a homogenization behavior for large loads. And you have to be very aware of this. And in fact, you can also think of this as an engineering opportunity. And that's what excites people about metamaterials, that you can engineer very nonlinear stress strain behaviors and therefore use it for energy absorption and so in impact bracing, right? It's really this this failure of homogenization at large deformations. Questions? Okay. So now let me move on to a bunch of examples which are on time-dependent problems. So the first problem I'll talk about is wave equation. It's basically the standard wave equation, linear wave equation, hyperbolic equation. So if I were to write it in the case of kind of solids, it would be the following. C would be the elastic modulus. This would be the displacement. So that's your equilibrium equation. Okay, you can do the two-scale expansion, and you can show that you can replace the solution of this with exactly the effective modulus and the effective density. The effective density is just the volume average density. The effective modulus is exactly the modulus that you did. So if you did the two-scale expansion, what you find is that there is nothing new in the wave equation. But there's something kind of strange that happens if you look at the energy. If you look at the total energy in the system, that's given by this, right? So this is the kinetic energy, this is the elastic energy. And the wave equation conserves energy, so it should be completely given by your initial conditions, U and V, right? So this is at any time t, and that has to be given by exactly the final energy. So now let's look at the homogenized problem. So this is the energy of the solution of this problem. Again, this is a wave equation. There's conservation of energy, so that should be exactly equal to that determined by the initial condition. However, you know that, so if I have some kind of uniform initial condition, so gradient U is uniform, this is nothing but the volume average conductivity or elastic modulus. And we know that that is actually strictly larger than the modulus given by C star. So what we find is that somehow we have lost some energy. This is the energy. So this is the energy in the original problem. This is the energy in the homogenized problem. So homogenization led to a loss of energy. So this can't be totally the right answer, and you're dealing with a wave equation where there's conservation of energy. So what happened so we basically violated conservation energy by homogenizing. So what happened? Anybody? Why did I lose energy? So the reason you lost it is because when you do this two-scale approximation, you're basically saying that your solution is going to be smooth compared to the length scale of the microstructure. So you're really doing a long wavelength approximation. So this solution describes forcings which are long compared to the microstructure, right? But in a wave equation, if it's a heterogeneous material, you can have waves bouncing around, so you can have a lot of different kind of wavelengths, right? It's not only the large wavelengths, but the small wavelengths. So how do I study problems? What happens when I really study problems when I have short wavelengths, and those are important? So let's actually look at it. And now I'm going to do one-dimensional equation. So this is the equation. And right, so this is the density, this is the elastic modulus or whatever modulus you have. So this can also be waves, so acoustic waves in air. So you basically have this. But for now, I'm going to assume that this modulus is not uniform. And it's very important that I'm studying the periodic case and not the random case. Okay, so you do what you're taught. You separate variables, right? You look for solutions of which are functions of time and space. Plug it in, you'll find this is exponential. Then you get the equation which looks something like this. But then you realize that if you have a medium which is periodic, if I take n unit cells, that's also periodic, right? Your medium is also periodic with n unit cells. And therefore, you should look not only at one periodic solutions, U being one periodic, but U being n periodic. So you have to solve this problem. So to get a complete solution, you have to use U as a function of x, which is periodic with period 1, period 2, period 3, period n. So there's a very nice representation theorem. It's called Bloch waves, which says the following. If I have an n periodic medium, I can represent it in this way. I can represent it with a one periodic function and something which is sinusoidal on the period k. So this is Bloch. Actually, it's called Bloch waves, but it actually goes back to Floquet before Bloch, but Bloch used this in physics, and that's why it's called often Bloch waves. So what you find is that this is actually a representation for a general n-periodic function. So rather than looking for n-periodic functions, I can look for functions of solutions in this form, and that gives me this set of equations. So if I plug this in here and impose the condition that B is periodic, I get this set of equations. And you can show that this is a Sturm-Liouville system, which means that there is, so given any omega, there are solutions for each k, which is 1 over an integer, 2 pi over an integer. So you get a large number of solutions for each omega. And this relationship omega as a function of k I should have said it the other way. So given any k, which is 2 pi over an integer, there is a countable infinity of eigenvalues omega. So there's a complete set of eigenvalues omega square. And that determines all possible waves that can propagate through the material. So let's look at an example. So I have a two-phase material, material 1, material 2, and I've chosen such that these things kind of work out nicely. And in particular, if you solve the system here, you'll find the dispersion relation, the relationship in k and omega is given by this. And we plot it, I've plotted it here. So given any k, there's a whole bunch of omegas that you get. So what it tells you is this is the omega is the frequency of the wave, right? I mean, so if you go back here, omega is the frequency and k is the wavelength, right? Wave number. So what it tells you is that if you have a wave, the frequency of the wave and the wave number cannot be arbitrary. They have to be given by those that satisfy this relationship. That means the only waves that are allowed to propagate are the waves which have wave number, frequency and wave number given by these curves. So notice something. So if I have a wave packet, kind of the effective wave velocity is given by the tangent. It's called the group velocity. So this is in the long wavelength limit. So when k goes to 0, you find that this is, and this is what we would have found by kind of the long wavelength homogenization. So it's consistent. But what is really interesting is you see that there are frequencies in which you cannot propagate any wave. So this medium, this periodic medium cannot sustain any waves. It will not propagate any waves which have frequency in between here or in between here, right? And these are called band gaps. So what happens is if I impose a wave which has this frequency somewhere here in a band gap, this material, which is made of perfectly elastic materials, will suddenly start reflecting this wave. So by using microstructure, I've created a highly reflective surface. And this is used very heavily in optics. So a lot of photonics basically is dispersion engineering. All the field of photonics just basically is dispersion engineering. You're trying to create heterogeneous materials which have incredibly complex dispersion relations. There's an emerging field of photonics. Unfortunately, the length scales are very large, not particularly useful. But one of the great uses of photonics in nature and band gaps in nature is blue butterflies. Blue is a color that nature has great difficulty in making. Uh, Notice that the flowers which you think are usually blue are actually purple or some variation of indigo or something else, not perfectly blue. And the way butterflies achieve this is by creating a highly complex surface so the lights, the blue is in the, so you have band gaps at other lights, and the only thing that gets reflected, they have a band gap at blue, very sharp band gap at blue, so blue gets reflected and all the other colors get absorbed. So if I have a wave, so if I'm interested in wave propagation in a medium which is periodic, then you not only get the effective behavior at long wavelengths, but when the wavelength becomes comparable to the length scale of the medium, you get very complex physics. In fact, notice that the slope, which tells me how the velocity with waves propagate in this medium, notice that this is becoming slower and slower as my wave number becomes larger, which is a way of trying to slow down waves by creating heterogeneity. So when I have the wave equation, you see that the behavior is not only described by this effective properties, but you have to be worried. You have to kind of think about these complex dispersion relations that come about. This story is very different in a random medium because you can see that I'm really using the periodicity of the material in these calculations. In a random medium, actually, over long distances, the solution spreads in a diffusive fashion. And that's why somehow you get, so you get a very diffusive spread of the energy in a random medium. And that's going to be quite different. Okay, any questions?
Can you have a band gap if your medium is, if it's random? Or is that not possible?
I'm sorry, I didn't hear you. You were breaking up.
If the microstructure is like random, then can there still exist a band gap, or is that only like this period if it's going to be periodic?
So random is a very broad class, right? So if you really are, if you're really sampling uniform IID from a uniform distribution, then there is no band gap. So you can think of band gap as being lots of internal reflections causing resonances. And that requires a very precise periodicity. If you don't have precise periodicity, you break up these resonances, and that's why you don't get any band gaps. Yeah. So in random mediums, you typically don't have band gaps. Okay. Very good. So now let me move on to a second problem. And a problem which is very relevant to a lot of kind of mechanics, both in solids and complex fluids and other phenomena. So, okay, I'll start with a very simple 1D viscoelastic problem. So think that I have a 1D medium. So your displacement is u, x is the coordinate. So the strain is du dx. I'm going to assume Kelvin-Voigt viscoelasticity. So the stress depends on the elastic modulus times the strain plus a viscosity times the strain rate. Epsilon t is d epsilon dt or uxt. So this is really the strain. This is the strain rate, velocity gradient, if you're fluids, and this is the viscosity. So it's a linear medium with a linear elastic modulus E and a linear viscosity epsilon. And I'm going to ignore inertia. So I basically get d sigma dx equals F, right? So that's my equation. I'm going to assume periodicity, not necessary. You can do whatever you would like, but periodicity makes calculations easy. So I'm going to assume that this is one periodic medium. E and nu are periodic. Okay. So how am I going to solve a problem like this? So you notice that this is linear. So let's try to get rid of time by taking the Laplace transform. So if I take the Laplace transform, okay, I get exactly the Laplace transform. I'm going to assume F for now is independent of time. So I take the Laplace transform and I denote it with a hat. So there. So if you look at it, this looks like an elastic problem at each fixed x, right? Just looks like an elastic problem. Stress, S is fixed, so stress is proportional to the strain with S-dependent modulus. So let's fix S. We know how to homogenize this, and in one dimension, it's even easy. I can calculate the effective property as the harmonic mean. If I have a one-dimensional medium, the stress is uniform in the medium, so you could do uniform stress averaging, and therefore you get this is the effective property. So I know the effective property as a function of each Laplace variable S. So I can take the inverse Laplace transform. And in general, when you take the inverse Laplace transform, so in general, when I take the harmonic mean, it's not of this form. So when I take the inverse Laplace transform, what I end up with, not only an effective modulus and an effective velocity, but also some kind of infinite time history kernel. So let's actually look at this with a simple, very simple example. I have two materials with some length scale lambda. So I have E1 nu1, E2 nu2. I take the Laplace transform. And then I get basically, this is the effective modulus, right? It's a harmonic mean. So it's given by this. Right? It's a harmonic mean. So it's lambda divided by E1 plus S nu1 plus 1 minus lambda divided by E2 plus S nu2. So that's the effective property. So now I want to take the inverse Laplace. So I can rewrite it in this way. There's an E star, which is plus S nu star. That's what I'd like to write it as because I want to put it in the original form. But then there's an extra term. And if you actually work out the details, so if you take the inverse Laplace transform or look up your favorite source on Laplace transforms, you find that the behavior gives you this. There's an exponentially decaying kernel with some relaxation time t star, which is actually just the ratio of E and nu, square root of the ratio of E and nu. So basically, I started with a material which at every point just depends on the strain derivative, but the effective behavior has an infinite memory. It remembers all prior strain histories. Right? It's very bizarre. So my Local material only senses the rate, but my homogenized material remembers everything. What is basically happening is there's two different relaxation times in the two materials. So basically, there's a constant exchange of information, and therefore information takes time to basically get through the system, and that's what gives rise to this infinite memory. So you see that.
Kaushik, a
Yeah.
question,
Yes.
a question, a comment. I think this is really nice. So later in the course, I'm going to do Maurice Wanzig formalism, where
Yes.
we show that anytime you truncate a dynamical system, a Markovian dynamical system,
Yes.
the coarse-grained dynamics will have memory, right? So it's a
That's exactly right. Yeah.
fundamental property that I think
Yeah.
everyone has to pay. Thank you for bringing this up in this specific example.
Yeah, I was thinking whether I should talk about Maurice Wanzig, and then I said,
No, it's
I
coming in the
wanted to do
course.
one more example, so I didn't do it.
Yeah, no. Thank you so much.
No, but this is exactly right? I mean, and yeah. So you get this infinite memory. Now, one of the things that we do a lot in modeling in continuum physics, we don't like these infinite kernels because in the language, it's not Markovian, right? I mean, it depends if I were to kind of solve this problem incrementally, in other words, the response now depends not only on the current state, but also on all previous states. So if I were to discretize in time, every update will depend not on the current time, but all previous time steps, right? So it turns out that you can convert this into a Markovian system in this example by the following. So let's call this the variable xi. So this is really, I don't need the entire history. I only need this integral of the history, right? And you notice that this integral actually satisfies this simple ODE. So I can write my new constitutive behavior, the effective behavior, in the following way. It depends on an effective modulus, an effective viscosity, and some internal state variable. In this case, it's linear. And the state variable evolves according to this. So by introducing the state variable, which captures all the history, you have converted this kind of infinite memory system into a Markovian system. Of course, you have increased the dimension of your problem. So many phenomena that we're interested in mechanics, whether it's solids, fluids, go away from the standard solids and fluids, we represent using state variable theories. We use state variables all the time. And in a way, the state variable represents all the fine microstructural and history information that we have kind of ignored in our continuum models. And here's an example of actually deriving it from an homogenization. Not too many examples of this kind. So in n-phase materials, you have to have n-1 internal variables. If you have a general material, you can approximate it with an n-phase material. And in viscoelasticity, it's called the Prony series. That's a common approximation. Now, in higher dimensions, something interesting happens. In higher dimensions, you cannot always, so in higher dimensions, depending on your microstructure, you might have singularities. So the elastic module, you might have corners, and that gives rise to singularities. And that means that you cannot represent it with state variables, and therefore people use, so things decay very slowly at minus infinity, so the memory is really long term, and people use fractional time derivatives to model viscoelastic materials, especially when they're doing nonlinear complex fluids. Okay, so that's to me, this is a very interesting example. I learned this from Pierre Souquet, where you can explicitly work out the state variables. And as I mentioned, in many kind of, okay, so I'm going to skip this out. I had this example, but I'll skip this. I just want to mention that in many, many phenomena in solids and fluids, and here's some examples, you find that we use state variables. And it goes back a long way on Sagar, but I was actually recently told that Duhem had used a state variable formulation for some problem that he was solving. So one of the kind of open problems that we have in the field is when we do this models, we basically prescribe what the state variable is. So in plasticity, you might prescribe that it has to be whatever the state variable is, right? Plastic strain, hardening variables. Can we discover this from some lower level physics? That is something that remains kind of an open problem and a problem that we can try to understand. It's really the topic of current research. So I want to now come to, in the final 5 minutes or so, come to the final example, and that has to do with pinning and depinning. But let me pause here to ask if there are questions about, sorry about giving you a headache, but about this example.
Thank you. I have one question on this last really interesting temporal integral.
Yeah.
So basically, from a physical point of view, by increasing the state dimension, we are splitting what originally was a material into two materials. I understand.
No, that is not, I mean, that's not how I think about it. The way I think about it is if I have a composite medium,
Mm-hmm.
the effective behavior is given by, is not Markovian, there's history dependence.
Yes, yeah.
And by introducing a state variable, I am converting the history dependence into a Markovian system.
Is because I found this really equation really similar to the Fano problem that it's really typical in quantum mechanics. And one of the issues that they were doing with these two systems is that they were not doing the Laplace transform. So they were always keeping, for example, the interaction between the medium, let's say an X-ray and a gold plate, as two different states and two different materials. And once you assume that the memory of the X-ray affects the state of the electron in this gold plate, then this Laplace transform arises, and you go from two ODE to one the sigma t equation. No, so it's interesting how the quantum mechanic, in order to go from the discrete to the continuum, needs to assume that the memory is part of the state, but you are saying that the memory has to be a state itself. So it's interesting, the direction.
Okay, so when you go from discrete to continuum, you're basically doing some kind of homogenization. And that, okay, so I don't know the example that you're talking about, so I can't comment specifically, but let me make the following general comment. When you go from discrete to continuum, you're basically doing a kind of homogenization. You're doing a truncation again, right? And for that reason, you end up introducing memory. And so the discrete system may not have memory, but the continuum system will. And very often, people just introduce some kind of state variable rather than trying to work out all the details of the infinite memory and then see whether you can do a state variable approximation. You just model it by a state variable. So I suspect that's what happens in the example you're talking about. Unfortunately, I don't know the example, so I can't tell you specifically, but that's what I suspect is happening.
And only one note on this. Do you think this could be related? Because I know this is maybe a complex problem, but in the case that we have a cycle, but that cycle may be infinite, I know it's a pretty kind of a strange problem, but do you think this could help also through this approach of memory?
Yeah, so this is very, very interesting, right? I mean, so you're talking about dynamical system where you have some kind of complex attractor.
Yeah.
And then a state variable may represent some behavior of the measure on the attractor. Yes, there are examples of that kind.
Okay, thank you.
Yep. No, good question. Very good question. Okay. Okay, this is my favorite example of all. I'm sorry I left it to the end, but okay, very good. So I'm going to have okay, so I'm going to, now that so let's think of as some kind of free boundary problem. So I have a bar, one-dimensional medium, I'm pulling on it, and there's some defect at position S. So you can think of it as dislocation, you can think of it as phase boundary, whatever. And a typical model we would write for this is the following. ds dt is some driving force. And what is a driving force? There's some kind of applied load, and there's some material resistance. You might call it back stress, you might call it whatever, right? So you get this kind of viscous evolution, ds dt equals sigma minus sigma r. Now, if the material is heterogeneous, the resistance will also depend on the position, right? So what would I do? Okay, I know the velocity, so I can try and integrate it forward. So I know the velocity, so I can say, okay, what is the time it'll take me to go through some length? That's this time. So the average velocity is given by this. So just a calculation, right? So I get the average velocity of this interface. Now there's something very strange that actually happens. When I did this, when I integrated it, basically I assumed that sigma was always greater than sigma r, right? It was ds dt, so I wrote it as ds equals sigma minus ds divided by sigma minus sigma r equals dt, integrated it. But in order for me to integrate it, I have to assume that sigma is always greater than sigma r, or sigma is always less than sigma r. But what happens if it is in between? Because sigma is the load that I'm applying, and sigma r is my material. So you see that what the correct interpretation is, okay, so what happens? If sigma happens to be exactly equal to sigma r, so this is sigma r, this is my applied sigma. If sigma happens to be equal to sigma r at some point, the velocity is going to be 0. So you'll have an infinite time, so actually the effective velocity is going to be 0. So I end up with some kind of stick behavior, right? So as I'm pulling out of it, the interface will move to a certain point and will get stuck there. So though the original behavior is linear, the effective behavior is not linear. In fact, you can do some asymptotics near the interface, right? You can do some asymptotics when sigma is close to the sigma max. And you can show that actually, if you're close to these kind of peaks, close to these kind of stuck regions, the behavior looks like this. There's a power law. And the power law is less than 1. So in fact, you're emerging from here, this slope is going to be infinite. The idea is the following. Basically, when your applied load is close to a maximum, the time it takes is really dominated by this position, right? The time it takes to navigate it. So if you're stuck in traffic, it's not where you're moving fast. It's the place where you're stuck that determines how fast you'll reach your destination, right? So that means that you end up with a power law which looks something like this. Okay. So you really get stick-slip behavior. So my material behaves in a viscous fashion, but the effective behavior is this kind of critical state behavior. What is worse is notice that this critical state really depends on the extreme statistics, right? That's what I meant. So the extreme statistics, averages don't matter. It's really the extreme statistics. So it's the tail wagging the dog, right? I mean, it's the end that matters. And you can think of this as a real opportunity. So that's why these are very hard to characterize, because extreme statistics are hard to characterize. But it's also a great engineering opportunity, right? So because you can really, what it says, because you can keep the average behavior the same, but change the effective statistics, and that has a profound effect on this. So I'll end with one realization of this, and that is my favorite, peeling tape. So I'm trying to peel tape, and there's this kind of famous Rivlin formula, which says that the force you have to apply depends on the stickiness of the tape, which is G, and some geometry. So I'm going to make a tape which looks like this. There are two segments. So this two segments, one which is thin and one which is thick. And in fact, to do this experiment, what we did is we took one tape and we piggybacked little segments of tape on top of it. So the stickiness of the glue, G, is exactly the same. When I try to peel it, here's what you get. According to Rivlin, these two tapes behave exactly, this is the peel force you need. But when you try to peel this, you see that the peel force you require is about 6 times higher than the peel force of the original tape. So I've increased the stickiness of the tape without having done anything to the glue because I have introduced some heterogeneous elasticity. And so in fact, I've changed the effective adhesive strength without changing the glue. So, and that is really an example of the stickiness. The other second comment I will do is the following. Very often when we do microscopic theories, we assume that the evolution is proportional to the driving force. So it's a linear law. But when we do macroscopic theories, microscopic theories like dislocation will say that the dislocation velocity is proportional to the P scalar force. But when we do plasticity, we have a yield kind of behavior. And that is because homogenization really creates this kind of stick-slip phenomena or this pinning phenomena, and the homogenized behavior is completely dominated by the pinning phenomenon. And again, the periodicity has nothing to do with it. It's really the statistics of the distribution of the defects that determine all of this behavior. So I think I'm run out of my time. And so there's some interesting examples. So here's a summary of what I talked about. And so I'm going to stop there, and I have some more time if anyone wants to stay on and ask questions. I'm happy to take questions.
Yeah, thank you so much. I think we've come to the end of the lecture,
Yes.
but yeah, students have 3 minutes to get out of class. So
Oh, I see. Okay. So sorry, I kind of.
no, this is fine. This is amazing. I think you touched
Thank
upon
you,
so many
Karthik.
things that are fundamental to the class, which is, I mean, we are thinking of different ways in which models enter
Yeah.
the world, how things change at different scales. So I think it was a really nice exposition. But yes, students, please, if you have a quick question, you can ask now. But it was an excellent lecture. Thank you so much. We're going to review this lecture at some point.
All right. If it's helpful, I'm happy to share these slides.
Oh, yeah, it'll be super helpful.
Okay. So I will email them to you.
Yeah. Thank
All
you.
right.
And
Actually, I mean, I think this is an excellent class, and I'll tell the students that this is really, you guys are lucky to be exposed to this kind of range of ideas in a class like this. Yeah.
yeah, different disciplines. And thank you so much for contributing it to it, Kaushik.
Happy to do that.
Yeah.
All right.
Thank
I'll see you. Thank you, everyone.
you. Bye.
Thanks, Scott. Bye.
Bye. Also for students, we do not have office hours today because I'm on travel, but I really hope you enjoyed the class. Thank you.
Thanks, Karthik.
Yeah, thanks.